Can you hear me?
Sì,
Yeah.
sì, ti sentiamo, Mirko.
No, for some reason, after I put in presentation mode, I hear a voice saying muted, that I'm muted, but you can still hear me, right?
Yes.
Yes.
Okay, perfect. Sorry for the trouble. Yeah. So once again, thanks, Ilaria, for organizing this webinar, and thank you and to all the BI-REX team for allowing this event about AME. I would like to start with saying that this presentation, the target of this presentation is to present at very high level the technology with Nano Dimension, what is AME, and give you a little bit of ideas of what's the potential in terms of application. I will not be too technical, but I would like to give you an overview of what this technology can do, technically speaking, in terms of applications. So this is the agenda, Nano Dimension introduction. We will talk about AME, why, the advantages. I will explain the basics and the fundamentals about the technology, and I will show you some applications in different fields. So Nano Dimension has been founded in 2014 by a small group of 4 friends. A small group, but with a big vision, which was at that time to change electronics manufacturing industry, to change the way the electronics can be produced, can be manufactured, and can be designed as well, allowing, let's say, a different degree, an additional degree of freedom by using a fully additive manufacturing process. We are the inventor of the word AME. There was no AME before Nano Dimension. AME means additively manufactured electronics. And from 2014 and until today, a lot of things changed in the meantime. Nano Dimension is no longer a startup, is no longer a small company, but it's a group of companies today. And the vision is to become the digital and cloud manufacturing leader, providing Industry 4.0 solution in the field of AME, which was the original objective of the founders, but also today about precision AM, ceramics, metal, additive manufacturing as well, and also polymers, micro precision parts at micro precision level, plastic ABS-like parts. So these are the main milestones. As I said, company has been founded in 2014. In 2016, the company has been listed on the NASDAQ. The first machine has been released in 2018. And we went through 2 or 3 upgrades, let's say, of the machine until the latest machine, which is the Dragonfly 4 that has been launched at the end of 2021. In the meantime, as I said, a lot have changed, especially in 2020, 2021, when the company raised $1.5 billion at the NASDAQ through a secondary public offering. And as you can imagine, with a big vision and a lot of money, you can really do a lot of things. And everything changed from that point. We started also M&A activities, so strategic mergers and acquisitions. We acquired the Nano Fabrica for the manufacturing of micro precision level plastic parts, ABS-like. We acquired the Deep Cube and other companies as well, as this slide shows. In particular, we acquired SM Tech, that is a Swiss company that makes pick and place and dispensing machines for surface mounting. As I said, Nano Fabrica for micro precision plastic parts, Admatec for ceramics and metal 3D precision 3D printing, GIS for global, which is global inkjet systems for the ink delivery, which is the ink delivery system that we basically use on the Dragonfly 4, and Deep Cube, that is a company I would like to spend a couple of words, because it's a company 100% owned by Nano Dimension that is developing artificial intelligence, and in particular deep learning algorithms that are now being integrated in all of our machines, including Dragonfly 4. And this artificial intelligence will allow to improve itself after printing, printer after print. And the objective is to improve the yield, print faster, increase the throughput, but also reduce the waste, reduce the cost and the energy consumption as well. So this is very important. This slides is just to show you and explain me to transfer the message of what is our mission. And then it's an analogy with the printing industry that's started a long time ago, writing books by hand. Then the printing press, industrial printing press came with more and more complex high volumes, high capacity machines until today, where books are mostly exchanged all over the world using digital files like PDFs and are printed locally. Nano Dimension mission is to do something similar for electronics. So instead of using an analog old process to print your designs, I don't know, probably in China or at any third party, we want to change the paradigm, providing a solution that combines a lot of steps in one machine only, that it's able to convert digital designs in functional electronics on demand, locally, anywhere in the world. And that could help, for instance, to cut trade and transportation by 40%, as shown in this slide that has been provided by DHL. The source is DHL here. So imagine the advantage from environmental point of view, for instance. Talking about PCB manufacturing, it's well known that it's an old process, analog process, which involves a lot of different steps, a lot of different machines, and it's extremely unsustainable process. Also, it's quite a slow process and requires typically weeks to prototype a new design until you have the design in-house. And also, it exposed the design, especially strategic designs, to risk for intellectual property theft. So our solution addressed these problems that I just described: excessive energy use, a lot of chemicals which are involved in the process, which of course causes a detrimental carbon footprint. How? This is just to show that typical cycle of prototyping, which normally requires that you exchange the files with the supplier, then they check the files, then they print and they ship, and you receive the boards typically in weeks. And as I said, you expose the design because you send most of the PCBs are printed in the APAC region. You expose the design, strategic designs, to risks in terms of intellectual properties. So our solution, it's extremely more sustainable in terms of environmental impact. We do not have waste because it's a fully additive process. We do not have chemicals involved in the process. We do not use water, and we only put material where it's needed. It's part of the process, additive process. It's faster. You can print a prototype depending on the dimension and complexity in a matter of hours or few days for different iterations instead of weeks. So imagine the advantage in terms of time to market and competitive advantage that you can get. And also, it's a secure by nature, let's say, because you print in-house instead of sending the design to third parties. Dragonfly 4 indeed combines over 70 steps into one single machine, optimize, of course, material usage, use minimum amount of energy, no need for transportation anymore because you can print everything locally, and of course it's secure by nature. But why ME and why now? It's not only a matter of sustainability, but it's also to overcome current technology limitations, such as could be performance, but could be also reduction of other important parameters, like, for instance, weight and size. Imagine, for instance, for satellite applications. This is just a slide to show few of the things that are possible with our machine. It's you basically have an additional degree of freedom. It's no longer there is no longer the constraint of a planar technology. So you need to stack layers, connect the layers using via holes, so drilling, electroplating. You can design, since it's a fully additive process, you can design your structure in 3D with the benefit of the additional degree of freedom, which means you don't need via holes anymore. You don't need drilling, electroplating. You can simply design your vertical or diagonal trace to connect the different part of the 3D circuit. We can print coaxial lines. We can print waveguides. We can print passive components like multi-layer capacitors, coils. We can print twisted pair connections. We can print shielding structures. So, for instance, you don't need any more via fences or stuff like that. You can entirely print a wall. We can print dielectric lenses and much more, actually. We can also use our technology for packaging, which means embedded die, embedded model MMICs, for those of you who are familiar, monolithic integrated circuits, without wire bonding. So we encapsulate the MMIC inside the structure, and we connect directly, printing the connections with our conductive ink instead of doing the wire bonding, which is a complex process. We talked about sustainability, but I want to show you just one more slide with few real data provided by a third party, not by Nano Dimension, which gives you some numbers. Now, we can argue if it's 94%, 92 or 96, but it's clear that there is a huge advantage, like 94% less CO2, 99% less waste, because basically we don't have waste except for the cleaning of the printing station. We don't have cleaning waste at all except for this. We don't use water at all. So huge advantages in terms of sustainability. From supply chain point of view, having the in-house capability gives you a couple of very important advantages. First of all, you do not need to rely on external companies. We had to face recently a lot of problems in the last years due to pandemic, due to nuclear disasters and so on, which caused huge issues to supply chains. It was really a disruption for most of the companies. Having in-house capability allow you to overcome these type of problems, especially for R&D point of view. And also, especially if you work in complex areas like packaging, there are very long lead times, which are due to very big players like Samsung, Apple, Tesla, which are using almost 100% of their resources. And so typically a single iteration requires 3-4 months, which is a huge amount of time. And with in-house capabilities, you can reduce this amount of time from months to weeks to prototype a package. Okay, everything fine, everything great, but how does it work? Our machine is based on inkjet technology. So everything starts from 2 inks that are combined together and printed using 2 different print heads that are inside the machine with 512 nozzles each. One print head is for the dielectric ink, which we call DI, which is an acrylic monomer. And the other one prints the conductive ink, which is based on nanoparticle of silver. Both the materials, the inks, are jetted. And so basically what we print are droplets. We are jetting droplets of 36 micron of diameter. And each layer we cure and sinter the 2 inks using the UV to cure the dielectric, and infrared radiation to sinter and dry the conductive ink. So after sintering and curing, we have solid layers overlapped one after the other, and resulting in a solid 3D structure. What we are printing, as I said, this is the process. I show you quickly. So the two tents with the two inks that are delivered to the print heads. The two materials are jetted. As I said, we are jetting droplets of 36 micron diameter. We jet the conductive ink, we sinter, and then we jet the dielectric ink and we cure using the UV. We do that layer by layer, and we grow up the structure in a fully additive way to achieve the final 3D object. How we do that? The machine supports Gerbers, ODB++, STL files, Excellons, and convert the 3D design in layers. So slices, the machine slices the design in layers of 1.25 micron of thickness. Each layer is basically a matrix of pixels, and each pixel is a droplet that we are jetting of conductive or dielectric material. We do that layer by layer, and we grow up the structure in this way. And as you can imagine, since it's a totally additive process, we can do a lot of fancy stuff like twisted pair connections, as I said, bus structures, multi-layer capacitors, without the need of drilling, electroplating. We just grow up the structure in a fully additive way, and we can have 3D connections inside. This is an example of a twisted pair, a real printed twisted pair, coils, and different type of connections, including coaxials. And this is an example with measurements of the coaxial line. This is another example just to show you where we replaced a field via a wall with just a diagonal simple connection. So big advantage in terms of performance and big advantage in terms of space, because we save, as you can see from the picture here, we save basically the space that it's normally occupied by the via wall. Why now? The technology maturity is the first point. Dragonfly 4 represents the 4th generation of our machine. So it's still a new technology, but it's quite mature. It's not the first machine that has been launched on the market. We are already at the 4th generation, and we believe we have reached really an excellent reliability point from hardware, software, and also from process point of view. We are developing new materials which will allow high performance applications for different type of fields. Third point, AME allows really to develop the next level of the electronics, the next generation of electronics, allows design that are simply not possible with conventional technologies. AME, it's something new, and it's something that will take time. Will take time to develop the competencies, and we believe that collaborations are key. Collaboration with competence centers, for instance, like BI-REX, to develop the know-how, and also accelerate the adoption of such kind of new technology. Some examples about applications. I will try to be quick on that without going too much in details. I just want to give you a broad overview of the capability of this technology, what can be done with this technology actually. So in this case, we have a couple of examples of RF filters entirely 3D printed, so without any other components to be mounted or encapsulated, which is based on multi-layer capacitors, 3 layers in this case, for the bandpass filter and the low-pass filter that you see here on the right. And few measurements as well, but again, I don't want to talk about numbers. This is an RF crossover. It's basically a coupler which is used to distribute RF signals for antennas applications. It's very simple design, but still it's 3D, as you can see from the video here. Something that needs a 3D technology like AME, despite it's a simple, but you need a 3D technology to do something like that. Antennas, we can easily print antennas and arrays. And here are a few examples, especially the structure you see on the right. It's a phased array antenna, and it's really a 3D, very interesting and complex structure, like pyramids, and behind each of these radiating elements that are on the pyramid, each side of the pyramid, there are 3D coils embedded inside. So it's this type of structures is only can be only realized with our technology, with an additive technology. This is an example of a phased array antenna, which is made of 3 different parts, which are assembled together using these small clips that you see here, for instance, and the holes that are here that are also 3D printed. And this type of assembly, it's very quick, very easy to do, and allows you, for instance, to use hair in the middle of the structure as a dielectric if you want to do, for instance, a very low loss antenna. On top here, you see there are dielectric lenses also printed to have a broader scanning angle in this case. And imagine that this structure has been printed in less than 9 hours, 3 parts printed in less than 9 hours, 3 samples. Here you can see before and after assembly. This is another concept. It's only the dielectric structure in this case. That's why it's only a concept. But it shows you this is a concept of an array antenna of Vivaldi antennas, for those of you who are familiar with antennas. And it's also assembled using clips that you see here on the bottom of the structure. We can also print flexible. If printed very thin, our dielectric material it's actually flexible. And this is an example of a linear conformal array with also dielectric lenses on top. And this has been printed in less than 6 hours. We can also do much more complex designs, like in this case, a metasurface, which is used to manipulate, let's say, electromagnetic waves. As you can see from the right picture, it's an extremely complex 3D structure. This is another example of an antenna. It's a metal lens antenna in this case, working at 75 and 120 gigahertz. This is just to show you that we can go also up in frequency and still getting very good performance, playing also with the geometry, like in this case, playing with the metal lens effects. As I said, we can print also flexible, and flexibility can be achieved by printing very thin, but also, like in this case, playing with the geometry. As you can see, it's a kind of matrix structure that has been designed to allow flexibility also for a little bit thicker structures, like in this case. Otherwise, when printed very thin, like in this case, here on the top right, we can print flex, rigid hybrids, assemblies, printing very thin, the dielectric. Printing very thin, I mean 250, 300 microns. And we can also print the so-called MID on the bottom right, the molded interconnect devices, like this example here. This is an example of a fully 3D printed drone, including the motors, actually. In this picture, you see only the stator, but we also have design for the rotor itself. And you can see the mesh structure here, the honeycomb structure, which has been used to reduce the weight, basically. This is another example of a micro drone, which is actually flying. I will not talk too much about this because it's one of the applications that Professor Pliva will present later, but just want to show that our technology is also used and for medical application, for health applications, and this is one of the examples that Professor Pliva will probably present much more in detail later. It's a bioreactor for cell cultivation. Other developments, totally different field, 3D printed loudspeaker, because when printed very thin, as I said, it's our dielectric, it's flexible, which means we can print kind of membrane. And with the membrane, we printed a 3D loudspeaker, entirely 3D printed with our machine. I will not talk too much about the flux gate sensors as well, because it's another application from Technical University of Liberec, Professor Pliva. But basically, this structure has an embedded core of Vitrokov inside. Other developments that the project that we are developing in these days, let's say, are also for optoelectronics. We are testing the possibility to transmit light inside of our dielectric material. And we are doing now testing for these time of flight sensors embedded in our dielectric. We are measuring the transmission, characterizing the transmission of light inside our dielectric material. For optoelectronics application, it's worth noticing that we can easily print lenses, and which means we can easily manipulate a laser light, for instance, a beam of light, printing the lenses. We are also working on MEMS, and this is another example, a collaboration with Politecnico di Torino, of a printed inertial sensor that has been presented at the IMAPS last year. I will not talk too much about that as well, since Vincenzo will probably show you more in detail this project. But however, this is a very nice example of a highly non-planar structure packaging for a neural interface with multiple functions that IIT developed using our machine. Another example from IIT, this is a piezoelectric ultrasonic transducer package with an embedded die, and thanks to the flexibility of our technology, IT was able to prototype different type of structures in a very flexible way. We have also projects in the space industry with L3 Harris. We sent this amplifier board to space for testing on the International Space Station. Prototype in less than 10 hours. So imagine the advantage in terms of time to market. Packaging and system in package development. Everything, let's say this was one of our, it's not really a package example, but everything started from this type of approach. This was socket and interposers. At first, we were thinking structures to stack integrated circuits instead of putting one beside the other. Stack one on top of the other and use 3D routing, as you can see from the X-ray image here, to interconnect the ICs. And the next step was to go into the complex heterogeneous structures, like in this case. This is one of the most complex we have done so far, I would say, which integrates DC signals, digital signals, and also RF. Coaxial lines and different components are encapsulated inside this structure, which is a PLL board. You can see from the video here how complex is this structure. And from the X-ray on top right as well, you see the X-ray images of what's inside. And this is a couple of sections of the structure to see what's inside and how the final product looks like. We also did system in package for RF. This one is, for instance, it's an X-band system in package for watt, which includes different dies, so different MMICs, different components, active and passive components, and a QFN pattern on the bottom. It's just because in this case we wanted a QFN on the bottom, but theoretically you can design what type of interface you like, because for us it's 3D technology, so you can have connection all around if you want, on top, on bottom, on the sides as well. This is the design and the components that are included inside. As I said, we printed the QFN, the main 50 ohm line, and the shielding walls in this case for RF, to shield the RF signals. Another application of packaging for power electronics in this case, this is a GaN-amped 650 volt, 60 amps, which has been packaged using our technology and we compared the measurements with the commercial package as well. And you can see that measurements are pretty much aligned with the commercial package. And this was the first attempt. So it was a very successful project in collaboration with RISE Research Institute of Sweden that was presented in the frame of Ultimate GaN project. And this is the module that includes 4 of the devices I showed you before. 4 of these included in one big module. And we 3D printed this module successfully. And again, it's 4 650 volt, 60 amp each. And this has been defined as the smallest high power module of its kind, which is approximately 64% smaller than any other smallest device, similar device with similar performance existing on the market. And this is a comparison with the conventional module they had before our technology. So we achieved 80% reduction on XY and 80% reduction in the 8. This is the last example, and it's really something that it's at the edge of what can be done today with our technology. I told you that we are printing droplets of 36 micron diameter, and this is a 3D printed bonding for an image sensor with connection of approximately 1 pixel size, with 1 pixel size spacing. So this is really, was a successful at the end, but was very complex project that we did, and it's at the moment at the edge of what can be done physically with our technology. Thank you. Any questions?
Thank you, Mirko. Exactly. Do you have any question?
So either I was too clear or maybe not so much.
I'm good, thank you very much. So this was pretty elaborate. So
Okay, if no one asks question, I invite Engineer Pliva to share and present his works.
Hello, Ilaria and gentlemen. I would like to share my presentation. Please confirm me if you see it.
Yes.
yes,
I see.
So I will show you some figures and some results of our research, which is based on AME technology and especially on a Nano Dimension Dragonfly LDM2, which we have in our university. At the beginning, a few words about me. Since 1997, I'm with Technical University of Liberec. I'm a member of Faculty of Mechatronics, Informatics and Interdisciplinary Studies. And before that, I was employed in the company Electron, and I was responsible for printed circuit boards manufacturing, especially for data preparation. And that's the reason why I try to continue with such expertise also till now. And I'm glad that we have this machine, and we are able to do some interesting designs and interesting research. Liberec is on the really north part of Czech Republic, close to the border with Germany and Poland. So it's easily to contact also our colleagues in these countries. Our university was established in 1953, so last year we celebrated 70-year anniversary, and my faculty was established in 1995. We provide bachelor, master, and doctoral study programs. We are a public financed university, research-oriented, and in comparison in Czech Republic, we are medium-sized university with more than 1,200 employees. I can mention that at this moment we have more than 10% of students from abroad, from more than 40 countries all over the world. So mostly I will speak about the results from the Dragonfly, but it is not the only equipment which we have or which we use for printed circuit boards design and checking the quality. So we also can provide some three-dimensional inspection in industry CT machine, Metrotom. We also do some cross-section analysis, spectral analysis, and some analysis of the surface of different materials, for example, for printed circuit boards. We use Autodesk Eagle software and Altium, and for fully three-dimensional design, we use Inventor and Fusion 360, and we also have some other tools like SolidWorks, Creo, MATLAB. We use Campus-wide license and other software like ANSYS and Statistica. Now I will present a few results from our research. First was motivated by our colleagues from Faculty of Textile Engineering, and it was motivated by exchange the glass-made bioreactor to prepare some our own design, which would be cheaper and more flexible in the design of the electrodes point of view. At this moment, electrical stimulation of the cells is a very trendy approach in cell culture because it can enhance the cell proliferation, orientation, and also differentiation of the stem cells. And for electrical stimulation, it's really essential to have a biocompatible and conductive scaffolds and also bioreactors. So we try to use printed circuit board as a bioreactor. In the well, we place nanofibrous scaffold, both in conductive or non-conductive character. And on the top of this scaffold, we seed the cells. And with help of the connected control system or equipment, we are able to create some electrical field between the tracks And these tracks are realized by CI silver ink in the bottom of the bioreactor. In the first experiments, we used the comp design where the wires were 100 microns, but at this moment we try to redesign it to another shape. And after that, we monitor the cells' behavior, like profilation, change of the cells' morphology, orientation, and some differentiation of the cells. At the really first beginning of the research, we have to assure ourselves that the materials are compatible with such experiments, so especially that they are cytocompatible. So we use MTT test and some standard ISO tests to be sure that the materials are appropriate for cultivation of the cells. So at this moment, we are sure that these materials are acceptable, and at this moment we try to make some next correction in design. So as I have already said, we change the thickness, track width, and geometry of the tracks. And next time we will change or design some different parameters for electrical stimulation, for example, change the voltage, frequency, and so on, and also in vitro parameters. That means cell density, cell type, cell media composition, and so on. So at this moment, we are designing a new bioreactor design. We use matrix design because we have to assure that statistically the cells behaves in all bioreactors in the same way. So you can see first print because at the beginning we don't want to waste for bad experiments the inks. So at first step we print only 4 bioreactors, and now we are printing the whole plate, and I hope next week we will make first experiments with the scaffold and the cells. Yeah, and the second experiment, it's really a few days or hours old. So we were asked by our colleagues in the Faculty of Health Studies and from a regional hospital in Liberec to make some equipment which can improve their measurements, or they experiment with pacemaker, because the pacemakers are shielded wires which are connected to the pacemakers too, but especially the top of the electrodes are not shielded. So sometimes the signal from electrodes is jammed by some external electromagnetic field, and it is not monitored anyhow. So the susceptibility of jamming is on the top, as I already said, especially on the electrode which is placed on the muscle close to the surface, to the body surface. And we discussed also with our colleague which makes some it's hard to say experiments in the brain, but it's true that the situation is the same. If they have some electrodes in the brain, they need to know the map of the electromagnetic field around the people. And it's also true that sometimes the people complain that their pacemaker doesn't work properly, and we know that they work in some workplace where is big electromagnetic field, and we have to know which field it is, how it looks like, and we can measure it, and especially in some wearable representation of such a sensor. So this is first result of the sensor. It is the thickness of the sensor is 2 millimeters. It composed of 10 conductive layers. That means insulation thickness layer is 200 microns. There are 8 turns of coil in each layer, and the thickness of the conductor is 17 microns. So these coils in each layer are connected in serial, and external size of this sensor is in the size to self-adhesive ECG electrodes, because we would like to implement it in this technology, in these standard sensors, and make some measurements on the human body. So thanks to this technology, we are able to use the three-dimensional space in a very good way, and we compare the result with the ANSYS model, and in comparison with this modeling, the results are really good. It is the serial induction was 27 microhenry, and the calculated value was 27.5 microhenry. The serial resistivity is 23.6 ohms. So what you see here on the right side, there is the photo of the sensor. On the right bottom, there is a model of 3 construction of this sensor, and in the middle, on the bottom, there is a cross section of this sensor. It's I think 2 hours old figure, so sorry for some scratches on the surface, but there wasn't time to make it better, and I hope for next presentation it will be better. So this sensor is linearly dependent on the frequency. It's very acceptable for large range of field of amplitude from millitesla to Tesla. It seems to be fault tolerant, so it's indestructible by external magnetic field. So it's also advantage for such a design. This technology provides high winding density in the used volume in a very small space. In the future, I think that we would be able to map external magnetic field around the human body, and at this moment we consult the possibility of clinical research and verification in medical practice. In future, I hope there will be implementation in some wearable application for monitoring such a EMC interference, and at this moment it's validated for non-invasive use in clinical research, as I already said, in cardiac center of our hospital. For next generation of such a sensor, I think that we can reduce the probe thickness. That means thickness of the isolation layer in z-axis. Alternatively, we can prepare also some capacitive sensor with this technology. and as I already said, future application in neurology department of the hospital. Yeah, so final part of my presentation is focused not for medical application, but I think that's also interesting. That means printed the flux gate sensor. So the main idea was to replace a standard PCB manufacturer technology based on FR4 material to the printed version. So our idea was to print some cavity in the sensor, then put a metallic ring inside this cavity. It was made by Vitrokov. Then fill the gap between printed material and core of the coil, and then continue with the printing process and to close the windings around the core of the coil. Here you can see the first version of the core, and here you can see model. It was realized in 4 printing steps. First was the bottom part of the coil. The second part was preparing the cavity in the sensor, then put the core inside the sensor, and after gluing it and filling the gap, to continue with the printing of the rest of the sensor. It was realized in a very close cooperation with our colleagues in Nano Dimension in Israel, and we use some standard quick non-conductive chip glue to fix the core inside the cavity. And here you can see photos of such a sensor, and we have to assure that the results are more than expected. The behavior of such a core is very challenging for next generation. So at this moment, we prepare ring core to the racetrack geometry to increase the sensitivity and replace the pickup coil by additional layers. So at this moment, on the right side, you can see the last version of the coil. Unfortunately, the results are not as good as we expected because there are some shorts in the printing process. So we have to redesign the measuring coil, and I hope that next generation would be better from the quality of the coil point of view. So finally, I have to thank to Nano Dimension for support, especially the people from consulting team, Natalia, Mirko, Sven, Valentin, Rafael, Aviram, and so on. And if you find these topics challenging or interesting, I'm very looking forward for close cooperation also with you. So thank you for your attention, and if you have some questions, please don't hesitate to tell it just now, or here you can see some contacts to me, so don't hesitate to write me. Thank you for your attention.
Thank you, Professor Pliva. Congratulations to you and your colleagues for your works. They are very interesting works. Any question?
Yeah, may I ask a question? Did you pick up electric signal from the heart through the coil? Is that what the purpose was? The coil which you manufactured in the context of medical technology.
Yeah.
So you picked up ECG signals through the magnetic field, so the heart currents, or was it more to measure?
It is designed. It is designed especially for measuring the electromagnetic field outside the body to reduce the noise which is captured by the sensors which are inside the body, or if the behavior of pacemaker is not as good as the patients or doctors expect, to find the reason why the behavior is in a bad way. Because as I already said, some people complained that the pacemaker didn't work properly, and finally we found that he works in the space where is some electromagnetic field. So to be able to monitor such an external field, we design such a wearable sensors, and we would like to design it compatible with the used shape of the self-adhesive sensors.
Okay, thank you. I understand the purpose now.
Yeah.
Someone else? No question?
Okay. So again, many thanks.
Thank you.
Thanks.
Thank you. So now we can hear the presentation of Vincenzo Mastronardi.
Yes, okay. Let me just share my desktop. Sorry, I have just a problem of okay, I'm here again. A problem of sharing, I mean, of privacy and something like this. Okay.
Okay, now we can see your presentation.
Okay. Maybe you can see it in a good way. Okay, thank you, Ilaria, for your introduction. And I'm Vincenzo Mastronardi, and I'm a researcher at the Center for Biomolecular Nanotechnology of Istituto Italiano di Tecnologia, that is located in the south of Italy, in Lecce. And today is a pleasure to me to show you which are our recent results about the use of additive manufacturing technologies enabled by the Dragonfly unit for wearable in finding some solutions for our wearable technologies used in monitoring human physiological parameters. And this is just the roadmap of my presentation. I will give you a short introduction of the IIT network before going with.
Sorry, Vincenzo.
Yeah.
We also see the first slide now,
Okay.
because we don't see the presentation mode, but your PowerPoint.
Okay, so I don't know now how to fix this problem. Probably I can go in this way.
Yeah,
If it's
okay.
not a problem to you, maybe it's faster.
Okay, thank you.
So I was saying that Okay, I will show you. I will give you just a short introduction of the IIT network before showing you the technologies we developed for the human body applications here in our center at CBN. Before showing you how we use the Dragonfly 4 faced with some challenge, especially in terms of fabrication and packaging of our sensors before going to the final acknowledgement. So IIT is an organization that revolves around the central research laboratories that are located in Genova and a wider network of centers that are located all around Italy, and that collaborates with a relevant academic institution. Currently, IIT consists of 11 centers located throughout Italy, and especially our center is based in the south of Italy, in Lecce, a small city in the south of Italy, exploiting also a great and important collaboration with Università del Salento. But IIT also relies on some other collaborations worldwide, and especially we have 2 outstations located in the United States, thanks to the collaboration with the MIT, where we work in building algorithmic tools for the analysis of complex systems and high-dimensional data, and with Harvard, whose work is mainly focused on the development of technologies for experimental neuroscience, advanced neural computation, and translational neuroscience. So our research targets are mainly based on the fabrication of micro, nano, and micro technologies that are applied especially for biomechanics, nano diagnostics, and nanomedicine. But we have also facilities that allows us to go up to technologies for energy, harvesting, and also computation analysis. But especially I would like to focus the attention especially on the backend labs that are equipped with all the technologies that are useful to pursue the second part of the device and the MEMS devices that we fabricate in our center, starting from electrical classical standard electrical characterization, or analysis, vibrational analysis of MEMS devices exploiting laser Doppler vibrometer, or moving to the packaging of the single chip inside the chip carrier and related wiring for chip-to-package connection, as well as the characterization of the achieved packaging. So the idea is to create, we'll skip this slide because without any presentation, there are some animation included, so it's difficult to understand this slide. But the idea is to create a skin body electronics that allows us to have not only a sensorial system, a sensing system, but also an actuation system that allows us to acquire and achieve and detect physiological parameters from the human body and take the decision and the actuation in order to, in example, provide the correct or a robust therapy for the after the diagnosis, after an early diagnosis of the disease. And for this reason, we are trying to create a closed loop healthcare system that is based on different technologies that goes from wearable piezoelectric sensors for healthcare up to multifunctional neural interfaces with deep brain regions to MEMS piezoelectric devices for actuation, and also compact radio frequency antennas to establish the communication between our sensor and the standard readout electronics. So all these element of the closed loop healthcare system have some challenges, and one of this main challenge is exactly the problem related to the interface between the sensor itself or the communication element to the readout electronic. And we exploited the Nano Dimension Dragonfly unit to face with this problem. And one of the application I'd like to show you today, and is already mentioned by Mirko previously, is the packaging of tapered neural optical fiber interfaces with multiple functions. In our laboratories, we developed these multimodal probes that are used on one side as actuation element in order to control the brain function, exploiting different mechanisms such as optical or by temperature or for the drug delivery, but also it allows us to have a sensing element in order to read out the brain activity, exploiting different mechanisms such as optical, electrical, or chemical transduction method. But the main we based our multimodal interfaces on the optogenic activation of medium depth regions of brain, in example the L5 and L6 cerebral cortex and the CA1 part of hippocampal region, by using tapered optical fibers on which, especially at the tip, we created some windows, optical windows exploiting focus ion beam technology, from which we can provide the blue light to the surrounding brain parts. But we included also on the tip of our tapered fiber some electrodes, some metal electrodes, in order to acquire the signal coming from the brain as a brain response. And we fabricated these electrodes by using 2-photon lithography. That allows us to monitor the light stimulated or the normal neural response of the brain. So the main challenge in this with this application, with this device, is to find a way to read out the signal from the pads that are located on the top of the tapered part of the fiber. And the main challenge is related to the high non-planar nature of this device. For this reason, we exploited the Dragonfly 4 unit to build an electrical interface that consists of a homemade, custom PCB that allows on one side to attach firmly the optical fiber that is a non-planar device, so that the PCB has an housing for placing the optical fiber, but the PCB includes also some connecting some pads that are on one side used for the connection, for a direct connection with the pads located on the top of the tapered part of the fiber, and some soldering pads that are used to connect the PCB, this custom PCB, to a readout electronics. This is the first, let's say, release of first generation of these electrical interface that has two main problems. One is related to the manually gluing of the fiber into the recesses by using epoxy resin, and this reduces the robustness of the gluing and of the fiber itself. And the second problem is related to the connection between the connecting pads and the electrodes that are placed on the fiber that we initially fixed by using some a conductive paste. To overcome this problem, we engineered a second generation of this kind of PCB in order to have a self-aligned packaging, direct packaging of the optical fiber, and we engineered the steps of the protocol of the printing itself, including not only the printing of the PCB itself, but also a stencil all around the PCB that allows us on one side to remove the PCB, the first printing of the PCB to firmly attach the optical fiber to the PCB itself, and it acts also as a guide for repositioning the PCB. And this repositioning of the PCB is useful to have a self-alignment of the PCB with the new part, the new of the second step of printing, that includes the covering directly on the fiber. A covering that is made by both the dielectric ink and the conductive ink. The dielectric ink acts as a protective coating, a protective cover on the top of the fiber, and the conductive ink is printed directly at the same level of the pads located on the fiber. According to the number of the electrodes that are made on the fibers, we can anyway print different configuration of our PCB, starting from the configuration with a single electrode up to 4 electrodes, engineering the layout and the final design of the PCB itself. A second application that allows us to exploit the Dragonfly 4 is the realization of a self-aligned packaging of piezoelectric micromachined ultrasonic transducers. We build in our lab this kind of probe made on silicon with the purpose in order to use them for ultrasonic medical imaging or blood flow measurement and photoacoustic imaging. But again, the main challenge is to have the connections, the direct connections, electrical connections on the final device. One of the standard approach is to use the wire bonding for the connections, but we try to exploit additive manufacturing technologies allowed by Dragonfly 4 to print a PCB that allows us not only to embed firmly grab the die, but also to have some direct connections from the die itself to a base connector. So we designed this custom PCB and engineered as well the fabrication steps that starts from the printing of a base that includes a customizable connector footprint on one side, and on the other side we have an housing that allows us to place the silicon die, and includes also a bottom back reflection hole. In this case, the thickness of this first part of the base is up to 350 micrometers, allowing not only also high flexibility of the final package, but that depends anyway on the silicon die thickness. Then we stop the printing in order to place the silicon die on the built structures that still remain attached to the printing platform. And in this case, we can perform a self-alignment. We can achieve a self-alignment of the silicon die with the next layer that includes the top enclosure frame and the metal tracks that goes from the pads on the device up to the connection pads on the other side of the board. And these are the final, this is a picture that shows you the final packaging, couple of example of final packaging, allowing us to skip the wire bonding that is the standard and required for the connections, for the electrical connections, using a PCB whose total thickness is up to 550 micrometers. But we exploit the Dragonfly 4 from Nano Dimension also to develop and build some miniaturized 5G antennas that are made of silver ink, just the conductive silver ink, directly printed on alternative substrates such as polyethylene naphthalate. The idea is to develop compact 5G antennas that can be used for the as a compact interface in biochemical and physiological parameter acquisition and communication with the external circuitry. And for that reason, we developed two different kinds of antennas. The first antenna is an evolved flexible multi-layer patch antenna used for sub-6 gigahertz band of the 5G standard transmission protocol. And the second one is a planar inverted F antenna called PIFE that is more compact compared to the patch antenna. The first device is then the patch antenna, a multi-layered patch antenna that consists in two parts. The first consists in a patch and a split ring resonator that are directly built on a dielectric polyethylene naphthalate substrate, and the second part is the ground plane that is still printed on the same PEN substrate. Then these two parts are glued each other by using a very thin layer of polydimethyl siloxane that acts just as a sticking layer. But in order to achieve this antenna, we engineered the use of the additive manufacturing technologies in order to have a alignment of the antenna, the patch, with the split ring resonator. So the first step of the fabrication protocol consists in the printing of just the silver ink patch antenna that is printed on one side of the polyethylene naphthalate. Then we keep this the same substrate, but we mirrored it in order to print the self-aligned split ring resonator that is aligned with the patch antenna and the ground electrode that is on the free part of the substrate itself. Then we split the ground electrode from the remaining part of the substrate, and we attach the ground electrode and the patch antenna plus the split ring resonator by using the PDMS sticking layer. So this is a result of our picture that's showing the results of our device that shows high flexibility. And we tested the antennas in order to measure the scattering parameters and the radiation pattern that is in very good agreement with the results we achieved by theoretical simulations, showing us that the antennas is able to communicate, to work at a frequency of about 4 gigahertz, that is in the 5G communication standard protocol. We also developed a second kind of compact antenna that is the PIFE antenna, and we that has a planar design, so it's easier to fabricate, but we try to fabricate these PIFE antenna on different substrate, starting from the glass, as you can see from these pictures, but also moving on flexible substrate, especially on polyethylene naphthalate and on chitosan substrate. It is a very interesting and performing material. But the characterization in terms of radiation patterns of this antenna is still in progress. The last applications that was enabled by the use of the Dragonfly 4 is the printing of silver ink based electrodes for biocompatible piezoelectric chitosan based transducers. So we developed in our laboratories a wearable chitosan and silver sensor flex that are fabricated directly on glass substrate. So the first step of this fabrication includes the deposition of the bottom electrodes by exploding the Dragonfly Nano Dimensions Dragonfly 4. Then we deposit on the printed electrodes a coating of PSS interlayer that acts as promoting addition promoter for the chitosan to the silver electrode. It is a conductive material before peeling off the device from the glass substrate. Then we deposit the top gold electrode by exploding E-beam evaporation before achieving the wires and the connections to the final sensor that is showed in this picture. But the main point is that all the device we have developed in our laboratories requires, since they need to be used in very contact with the human body, they require a high degree of biocompatibility, and for these reasons we wondered if the materials we are using that are provided by the Dragonfly 4 are biocompatible. And we performed some tests, especially on the silver ink material, in order to assess the degree of biocompatibility of these materials. So we prepared a series of samples exploiting the same fabrication protocol of the chitosan-based devices. So we prepared 5 samples. The first one that is based on the chitosan of a bare chitosan film. The second one and adding progressively the materials to achieve the final device that consists of chitosan plus the P.PSS, the silver, the bottom silver electrode, the top gold electrode, and the pyridine that is a polymer for encapsulating, finally encapsulating the device. And we tested these samples by immersing them in different well in which is present a cellular medium that is the embryonic fibroblast coming from mouse. And we keep these samples immersed in cellular medium for 24 and 72 hours. Then we performed 2 different kind of tests. The first to assess the viability of the cells. The first was an MMTT colorimetric assay that is based on that is used to assess the cell's viability through the metabolic by observing their metabolic activities. And for this reason, this is why the cells were in contact with a reagent that is the tetrazolium salt compound. So viable cells, since viable cells contain oxidoreductive enzymes, they can react with this compound, producing a new materials, producing new products, that is the formazan crystals, that changes according to which also the color of the solution changes accordingly. So we moved from a standard pink color of tetrazolium salt compound to the orange color or formazan crystals. So we did just a visual inspections of the tested samples, as you can see from these pictures, seeing that the most, I mean, all the samples, all the tested samples from the samples number 1 to the samples number 5, that includes the silver ink, the Nano Dimension silver ink, allows have no effect on the cells, so we can assess that according to this colorimetric assay that we have a high degree of cells viability. But we performed also an absorbance analysis of the cellular medium in order to assess the percentage of cell viability. And after this analysis, we saw that all the samples, all the used samples, and especially the samples that contain the silver ink, have a high degree of non-toxicity, that is over 70%. It is the minimum threshold that allows us to assess that the material, the used material is completely biocompatible and can be used to fabricate full biocompatible sensors. So this is actually the last slide of my presentation. So I would like to thank all my colleagues, all the colleagues that are involved in this work, and all the collaborators, and especially all of you for your kind attention. So if you have any questions, please don't hesitate to tell me.
Maybe I have one. May
Yeah.
I? Thanks for your presentation, and I would like to ask, you use Dragonfly 4, yeah, that's it, and you print on the glass background.
What do you mean? So I mean, it depends. I mean, we print on glass background just for the for an application, for the antennas application.
Yeah, and
then
you peel it.
Okay, maybe you are referring to the Kaito-san-based sensor. Let me again share my screen. Just a few seconds.
Yeah, no problem.
Okay. Okay, maybe you're referring to the application, right?
Yes.
Okay.
Yes.
Okay, in that case, we printed the electrodes directly on the glass.
Yeah.
As you can see here. Then we deposit on the P.PSS interlace.
Yes.
That is conductive material, conductive polymer, before depositing the Kaito-san film, that is piezoelectric material.
Yes.
At this level, we can just peel off the device from the glass substrate, and as you can see from these pictures, the electrodes remain still attached to the Kaito-san that is all around here.
Yeah.
Thanks to also the help of the P.PSS.
Okay. What's the thickness of the printed part?
It's just, if I remember,
just a few microns.
Meters.
Okay. Okay. Thank you.
You're welcome.
I have a question also, Vincenzo, which is related to this question of Professor Pliva. Are you printing directly the conductive ink on glass, or are you depositing first maybe a very small thin layer of dielectric?
No, it's direct on the glass.
Direct conductive ink directly on the glass.
Material or without any modification, a surface modification also of the glass itself. It's just, I mean, the glass we used for the calibration of the machine.
Okay, so once you peel off the structure, the electrode is fully exposed to air.
It's fully exposed?
Exposed to the environment, to the air.
Yeah, exactly, yes.
Okay.
Yes.
Okay. Thank you.
You're welcome.
Thank you, Vincenzo.
You're welcome.
Any question to Vincenzo? Other people? No? Okay. Giovanni.
Yes. Good afternoon. Thank you very much for your presentation. I am Giovanni Cicceri from University of Palermo. So my question is about this very general case study. So how are the sensors and devices are connected to for computer for data collection and analysis? So this is my question.
You mean which kind of device are you referring to in example?
The wearable in general.
They are connected. Let me just
connected to for computer device. I don't know for data collection and data analysis in general.
Always done by interfacing the device with an readout electronics.
Okay, with the Bluetooth?
Usually use even custom PCB that includes charge amplifier or voltage amplifier, because usually we need to amplify, generally we need to amplify the signal, especially in the case of piezoelectric transducers, because sometimes the signal coming from the piezoelectric transducers is not so high, so we need to amplify it. So the point is that going from the sensor to a circuitry that includes amplification, that is includes an amplification chain before going to an example, usually standard acquisition systems, such as
okay,
oscilloscope or bench meters like multimeters or SAS meters.
Okay, thank you very much.
I would like to add a comment about this. Vincenzo, if I remember well, you also developed a meander antenna which was used to transmit the data wirelessly. Am I right?
Yeah. Yes, exactly. So this kind of meander antenna I have not reported in my presentation, but we did, and is built directly exploiting both the inks. So the conductive and the dielectric inks, yes, and but they have the same use as this kind of antenna, as the evolved multi-layered patch antenna or the PIFE antennas. They are used for communication, wireless communications. Yeah, the only difference is that in this case we have. We print just the conductive ink on alternative substrates, like as polyethylene naphthalates or chitosan materials.
Okay, thank you, Vincenzo. I think that are very good examples of how our technology can be used and how adaptable it is based on your needs. Like you showed these are the antennas for wireless communication, but you also showed slide 22 here, the other project where you designed the connector to interface as an interface, a custom connector. So I think both are very good examples about the flexibility of an additive technology.
Yeah,
thank you.
You're welcome.
Okay, if there are no questions, I think that we can hear about the last presentation by Engineer Tip.
Okay, so let me share my entire screen. Is probably the easiest way.
I see myself. Okay, now we can see your presentation.
Okay, very good. Can you see the entire screen?
Yep.
Okay, wonderful. Okay, so let me talk about Celtro and the project we have together with Nano Dimension. So I'm CEO of Celtro and also co-founder, and we have a team of 9 people at this point. So this is a mixed team of engineers, of medical doctors, medical technology people, and also finance and business development. So this is what we are trying to achieve is to fix problems in the for implants, for medical implants. So what we have today is batteries for pacemakers, also brain stimulation, other things. Batteries fail; they have to be replaced. And our initial idea was to say, hey, the power requirements are coming down all the time. Can we go without batteries? And so this is one of the vectors of our development. Can we remove batteries altogether? The second thing is leads. Leads break and they clog up and make terrible problems in the body. And can we get rid of leads? And then can we altogether harden the interface to tissue? So this was kind of like at the onset of our company and the founding idea. This is what was the pacemaker yesterday. So you see a pacemaker which is kind of getting implanted, typically under the left arm, and then there is another concept which goes through catheter directly into the heart. And what we want to do is take up on this concept and miniaturize it. So if you go and make it bigger, so you see parts with a lot of electrodes and needles, or here you find a lengthy part also with needles, conceptually speaking. So we haven't gotten that yet, but that's where we want to go. So why do we think we can do this? So this is the all-over-all chart in semiconductors. So power over clock speed. And what is the higher portion is computing, embedded. Wrist watches is probably the smallest piece you can find. But what we want to do is we want to go into the nanowatt area. And what I want to say with this chart is that typically these lines here are technology lines. So one technology has one line, and if you work at 10 watt in the gigahertz range, you can work at 1 hertz or 1 kilohertz in the nanowatt range. So that's physics. There is a leakage component on top, which I'm going to talk to in a minute. But dynamically speaking, we're already there. Today, the semiconductor industry builds chips with artificial intelligence running 1 teraops and consuming 1 watt. 1 teraops is 10 to the power of 12 operations per second. So if you scale this down by a billion, you end up with a nanowatt at 1 kiloops, and that's 1 kiloops. That's pretty cool. This is something which we could use. We don't probably need more than that. So Moore's law is our friend, I want to say. Then we have the chip electronics allows for multiple connections to the tissue, and we will have dynamic redundancy schemes on top of that. So with this, we don't have to invent new technology. Technology is there. We just need to make it use. There's one little problem, and this is called leakage. So up to 28 nanometer, you find, and you are probably not a semiconductor expert, so I'll be brief. You find a source, a gate, a drain, and the gate controls the current from the source to the drain. On top, there is a diode from the drain to the substrate, from the source to the substrate, and these make leakage. So there has been recently technology advancements which look like this. So there's now technology available which has a box, a body oxide, an isolation layer underneath the source and the drain. So in this context, the drain to substrate current is blocked by the oxide. So this is fantastic. So we have technology at hand being able to cut off the leakage current. Also, if you put this vertically, you call this FinFET, and this is probably leading too far if I elaborate on this, but we have FDSOI and we have leakage and FinFET reducing the leakage, and this is the technology we need to use. So, in fact, then we looked at biology. So human cells are like batteries. So there is, during each cellular cycle, there is a charge and a discharge. And This is kind of an replacement diagram where there is a kalium-natrium exchange between the inside of the cell and the outside of the cell. And what happens, if you look at the voltage inside the cell, you find there's a swing of almost 100 millivolt inside the cell. Now, we will not be able to access the inside of the cell because the cell is not stupid. It will kick us out. But we can access the outside of the cell and retrieve some of that potential. So how does it work? So as a matter of fact, we have said very simple model, one cell, 10 femtojoule per heartbeat, and it gives the direction to the next couple of cells, and those to the couple of cells. So there is an avalanche wavefront traveling through the heart, and already the left ventricle has billions of cells. So so there is plenty of cells and plenty of energy. The thing is, we need to just kick the initial cell. And we harvest from, this is here the red bars here, which you can see. So the essence is we need to harvest more than we need for stimulation. And this is what we are thinking now. What we need is an array of electrodes from where we can harvest energy, and we just need the right spot to kick the cells in view to initiate the next heartbeat. So, and this is the conceptually, so we haven't built that at this point, I have to say that, but conceptually, we have come up with a system like this. So we have a chip, and underneath we have the pins, and these go into the tissue, and the upper part here is in the bloodstream. Same over here. We have moved these pins around, and they are now at the top end of this kind of module. And just to elaborate on the size, this is a 10 euro cent coin, which plays into this just for perspective. So what we want to do is we want to work in the nanowatt power footprint. We want to eliminate the batteries. We want to eliminate the leads, because we put these contacts directly into the tissue, which gives us a pervasively redundant tissue interface. And of course, we want to deploy through catheter, which means through the groin or the arm, even vein, and that would make deployment really easy. So the thing is, if we are able to miniaturize, today the Micra is getting where this red flash is, so it basically is relatively large and has to be anchored in one of those main chambers. But if we are able to get smaller, we can go everywhere. We can even go on the left side of the heart, and that would be a big advantage, because today pacemakers don't do this, or do this only from the outside with a nasty trick. I'm going to spare you with the details here. So, but miniaturizing is really good, and we think with our concept we can do that also. Now we have developed. Now we needed at this point Nano Dimensions came into play, and we have developed a joint development plan with Nano Di. So the first phase, we were printing a needle holder. So basically, we have these electrodes from a supplier, and we need to assemble them into a package. And so the first thing is we print this needle holder. Here you see in the middle holes. It is 4x4, so 16 holes. We put the needles in there, and then we print over these needles. So which means, and it's hard to see, but what you find is, you see the needles here. They are covered on one end with the dielectric, and of course, Nano Dimension's capability is to continue printing with the liquid silver to connect this to further chips. So Nano Dimensions gives us an ability to go very fast on prototyping and hopefully also into medical qualification. So from then on, the next phase is to plan for prototype. So something which is, this is a flat shape, but we may also go on other shapes. We haven't decided that. We have completed phase 1 and phase 2 with Nano Dimensions, and we are about to enter phase 3 and also phase 4, where we can print then, if we can print 60 needles, we can also print 160 needles. And then we have about the size and electrode numbers, which we think we need. And then at one point in time, we will have to go into a package qualification and hopefully also get this qualified for into the medical domain. But that's future stuff, because we first need to prove the functionality and the energy autonomy. Once this is done, I think we, as a development plan, we do have time to care for that aspect also. So with this, I can show you a few things which we have printed with Nano Dimensions. So here you see soldering pads for little for connector. Here on the back side you find the pins. They look directly towards you, so you just they are circular at this point, but they are pretty sharp. And from the side you find the needles here. They're sticking out of the package, and on the front, on the other side, we have this connector, and the connection is being done from the needle to one of these connector pins. And on the other side, we fix this with we fix some flex cable, and then we go further. So basically, what we do is we have a header. We have a flex cable. We have on the tip here, we have what we get from NanoDi, but we also did some PC boards at this point. And but the NanoDi solution was is also working here. So then we have also done our electrophysiology management system. So this is an early version here which we used together with some other equipment and which does some recording. We went into mice and also other animals and then recorded what our signals, and also did pacing. So here you find the needle holder. This is a PC board thing fixed through a vacuum fixture, the flex cable taking in, and this is an animal heart which actually fixes from the outside. In the future, will be from the inside of the heart, but initially we do this from the outside. Also, what you can find here is this is the electrode array, which then goes to the header, which goes on to the measurement system. So once we are done with this, we can, and we have it proven on the heart, we could also do potentially go on other things. Incontinence is one of the things, hypertension, sleep apnea, deep brain stimulations. I could also imagine that glucose sensors for diabetes monitoring is also a thing. So lots of things once we are able to replace the battery, that we don't need to have replacement surgeries, but one implant once for life, and we'll be done. So with this, I'm already done, and I would like to thank you for your attention, and I'm open for questions. Okay.
Thank you.
Hi, Ilaria. Was I too quick?
Question?
Nano Dimensions, I have to add, Nano Dimensions helped us tremendously find a fast way forward here. So I think seeing the size, we would love to get to the first prototype, iterate on the shapes and forms, and then move forward also into medical qualification, because especially in medical technology, the form factor is very small, and the component cost is not so sensitive. So I think it's an ideal application area for AME technology. Okay. Thanks for your attention.
Compliments for your work. Very innovative mood to use this technology.
Yeah. Yeah, we also had an image film together with Nano Dimension. I don't know if you have seen it, but there is an image film also around on the Nano Dimensions website, also on our website, by the way.
Yeah, it's on YouTube as well.
Oh yeah, it's on YouTube also.
On our channel, yeah.
Yeah.
Yeah, I see the video.
To be together with you on this.
We are really proud to. If there are no further questions, I would like to thank Gerd, Vincenzo, and Professor Priva also for your work. We are proud really to work with innovators like you. Thank you very much.
Thank you.
Yeah, I agree with Mirko. I want to thank you all the relators to have accepted to join this meeting, this webinar, and to have shared your works and your research. Thank you, Mirko, for the help in the building of this webinar.
Thank you, Ilaria, and thanks to the whole BI-REX team for making this happen and for the organization of this webinar.
You are welcome.
Wonderful. Okay, so I'm going to sign off then. Thanks very much.
Okay.
Thank you.
Thank you, everybody.
Thank you, everyone.
Bye-bye.
Thank you.
Bye. Bye-bye.
Bye-bye.
Ilaria, you should stop recording.